This is lesson 8.5, divide radical expressions. The learning objectives are to divide radical expressions, rationalize a one-term denominator, and rationalize a two-term denominator. Now, in the previous lesson, 8.4, we talked about adding, subtracting, and multiplying radical expressions. So it makes sense that we would then focus on dividing, right? All four operations, addition, subtraction, multiplication, and division. And in fact, we've already talked about a property called the quotient property, and that property will be very helpful. We learned about it in section 8.2. All right, so the first time we encountered the quotient property was in 8.2, and it says that if the nth root of a and the nth root of b are real numbers, and b does not equal 0 because it's going to be in a denominator, right? So we can't let b equal 0. For any integer n greater than or equal to 2, then we have this scenario. So the nth root of a over b equals the nth root of a divided by the nth root of b. Okay, that is the quotient property. And so you could take a single radical with a fraction inside of it and split it into two radicals, okay, with the numerator going in the top radical and the denominator going in the bottom radical with division between them. Okay, so we're splitting from one single radical into two radicals using the quotient property. Quotient meaning division, right? Quotient is a fancy word for division. But not only can we take a single radical and split it into two radicals, we could go the other way. If we have two separate radicals in a fraction, then we could combine the two radicals into a single radical with the fraction inside, the numerator and denominators, pieces, those radicands. Great. So we're actually going to use this version of it today. So we're going to go from having two radicals and reducing to a single radical. And I'll go straight into some examples so you see this in action. Okay, so when I see 72x cubed under a square root divided by 162x under a square root, I think, well, I could take those separate square roots and combine them into a single square root. Okay, and when I do that, I then can have a fraction inside that I'm going to immediately reduce. So I'm going to take this information here. I'm going to reduce 72 over 162, right? That's a fraction that's reducible. And so I end up getting, let's see, I'm going to just compute this in my calculator, and I get 4 over 9. Okay, so 72 over 162 reduces to 4 over 9. And you'll be able to, do that in your calculator if you have large numbers to reduce. And then I look at the x cubed terms. Now, x cubed divided by x, well, one of those x's cancels, right? And sometimes it's good to ask how many more x's are on top than bottom or bottom than top. In this case, there are more x's on top than on bottom. There's 2 more on top. And so that's why I put an x squared right there. Great. And so now because I was able to take these two radicals and make them a single radical, I was able to reduce the ratio of the stuff inside of them, right? And I was able to simplify these big numbers into something much nicer. And now I can take the square root of all the things that are remaining. Okay, so I could take the square root of 4, the square root of x squared, and the square root of 9. Okay, and the square root of 4 is 2, and the square root of x squared is x, and the square root of 9 is 3, and I'm done. So it simplifies all the way to this. Well, that feels really good, that it simplified and we got rid of the radicals. So that's a great skill to have. When we see a radical divided by a radical, we can use the quotient property to combine two radicals into one, and then we're able to simplify further oftentimes. Great, let's try one with, instead of square roots, we'll increase the index to cube roots. And so here I have a cube root that I'm going to combine all of this stuff into a single cube root from these two cube roots. And while I do it, I'm also going to reduce the fraction. So when I see 32 divided by 4, I then reduce that to 8 on top, right? Because 32 over 4 reduces to 8 over 1. Okay, and I can make that 1 invisible because I'm going to be putting more stuff in that denominator. Now, when I look at the variable, right, on top I have x squared, on bottom I have x to the 5th, and I say how many more x's are on bottom than on top? In this case, I see there are 3 more x's on bottom than on top. And so on bottom I put an x cubed. And what's great is now my cube root, because I combined the 2 cube roots into a single cube root and I simplified the fraction of stuff, I'm left with this, the cube root of 8 divided by x cubed. And I can take the cube root of the numerator stuff and write the result, and then take the cube root of the denominator stuff and write the result. And the cube root of 8 is 2, and the cube root of x cubed is x. Done. Moving forward, and you'll notice I've already set things up, right? I'm taking a fraction of radicals, and I'm combining the 2 radicals into a single radical. So I'm already setting it up so that it's easy to just approach it. You can do the same. So here I see the square root of 147 times a times b to the 8th divided by the square root of 3 times a cubed times b to the 4th. So now instead of a single variable, we have 2 variables in question, a and b. So combining these 2 radicals into a single radical, I'm going to now simplify the fraction. I have 147 divided by 3, which gives me 49. And that goes on top, and 1 goes on bottom, right? So this is reducible by a factor of 3, and I get this. And now that 1, it's about to become invisible because I'm going to have other things. Now I look at the a variable, and there's an a on top and an a cubed on bottom. How many more a's are on bottom than on top? There are 2 more a's on bottom than on top. So that's why I'm putting an a squared on the bottom. Now I look at the b variable. B to the 8th divided by b to the 4th. How many more b's are on top than on bottom? There are 4 more b's on top than on bottom, so I put a b to the 4th in the numerator. All right, so at this point, I now try to simplify the things under this square root, and they're all perfect squares. 49 is a perfect square of 7. B to the 4th is the perfect square of b squared, and a squared is the perfect square of a. And so I can get rid of the square root entirely by writing 7b squared over a, and we're done. We have taken the square root of all those values, no more square root. Let's try another. So now we're going to move from a square root. We'll increase the index value from 2 to 3, so now we have a cube root. And let's combine these 2 radicals into a single radical. And that's a cube root, so I'm going to write a 3 there. Negative 250 divided by 2. That's what I'm going to simplify. And that gives me negative 125 divided by 1. Okay, so I reduced by a factor of 2, right? I divided this by 2 and this by 2, and I got this. And now that 1 is going to become invisible because it's going to be multiplied with other things. So I don't need to worry about that 1 anymore. Let's now look at the m variable. We've got m on top and m to the negative 2 on bottom. Now, little reminder for you, when you have a negative exponent, that thing can flip to the top of the fraction, right? It's on the bottom of the fraction, it's going to flip to the top, and that will make the exponent positive. So negative exponents, the way they become positive is by taking their reciprocal. If they're in the bottom of a fraction, they go to the top, and vice versa. And so I get m times m squared, which gives me m cubed. All right, so I'm going to write m cubed right here. That's how many m's I have. And now let's think about things in terms of the n variable. N to the negative 2, and then on the bottom, n to the 4th. And I see this negative power, and I want to get rid of the negative exponent, so I make it positive by flipping this to the bottom, and n squared gets written on the bottom with n to the 4th. So on the bottom, I have an n to the 4th already, but the n to the positive 2 power joins it, and n to the 4th times n squared is n to the 6th. So I'll use the product rule of exponents, and I've got n to the 6 right there. Great. And so I've simplified all of this, right? Combining the two radicals into a single radical, and then simplifying the fraction on top and bottom like we've done in past lessons. And now I can apply the cube root to all the things that are, products and quotients. So the cube root of negative 125, well, that's negative 5. 125 is the perfect cube of 5, right? And now the cube root of m cubed, that's m. And the cube root of n to the 6th is n squared. With these exponents, you just need to take the index, and divide it from those exponents. So the exponent of 3 divided by 3 is 1. Right, so there's an m to the first power, but of course we can make the first power invisible. And then the 6 divided by 3 is 2. All right, so this is this cool thing with radicals. We can take the exponent that we're dealing with, divide by the index value, and that gives us our new exponent. All right, we got our answer right there. Next, let's try one more of these babies. So when I see the square root of 54x to the 5th y cubed divided by the square root of 3x squared y, I'm going to take these two radicals, these two square roots, and put them into a single square root. And I'm going to simplify, the coefficients, and then the x variable, and then the y variable. Here I go. 54 divided by 3, well, that comes out to 18. Okay, so I've got 18 over 1. 54 over 3 reduces to 18 over 1. Okay, now let's look at the x variable. X to the 5th over x squared. None of the exponents are negative, so I don't have to worry about that. So how many more x's are on top than on bottom? Well, there are 3 more x's on top than on bottom. So I put an x cubed on the top. Okay, now moving on to the y variable, y cubed over y. How many more y's are on top than on bottom? I'll put a y to the first power so you see that first power. Well, there are 2 more y's on top than on bottom, so I put a y squared on the top. Great. Okay, so here is my result. I'll just center that 1 a little bit. It looks nice. Okay, so this is what we got. And what I love to see about this is that we have division by 1, which we can make invisible, right? So it's simplified so far that we don't even have a fraction anymore. We just have the square root of 18x cubed y squared. Now, we've also not just learned about the quotient property, we've learned about the product property, which says that I can split a square root or any root into 2 different roots. Okay, this is called the product property. I can go from a single square root to 2 square roots with multiplication between. Product means multiplication. And then we break up the pieces into their perfect square stuff and then the leftover stuff. This is an ability you learned about in lesson 8.2. And so when I see 18, I think of perfect square that 18 is a multiple of. Right? 18 is a multiple of a perfect square. What is it? Well, that perfect square is 9. And the leftovers, that's 2, because 9 times 2 is what makes 18, and 9 is the perfect square that I was looking for, and 2 is the leftovers. Great. Let's now move on, and we're going to consider breaking the x variable into pieces. Now, if it helps you, make the index visible so you can see, hey, we're trying to put perfect squares, perfect powers of the index in the first radical. And so it would make sense that I would need my x variable to be the index value or a multiple of the index value. 3 is not a multiple of 2, so I can only put 2 x's in this perfect square radical, and then the leftover is x. Now I move on to the y variable, and I've got y squared, and 2, the exponent, is the same as the index value, so it's a perfect square, right? So I put y squared in the first radical. And because I've done this, okay, I can now simplify the first radical. The square root of 9 is 3, the square root of x squared is x, and the square root of y squared is y. And then I multiply on the leftovers, right, which are stuck under the root. They can't come out of the square root, they're stuck under it. So I have my solution of 3 times x times y times the square root of 2 times x. That is my answer. Great. Now, we are now going to move on to a new objective, and that objective is to rationalize a one-term denominator. Okay, so before we talk about rationalizing a denominator, let's bring up what it means to have simplified radical expressions. Okay, a radical expression is considered simplified if there are no factors in the radicand that have perfect powers of the index, no fractions in the radicand, and then no radicals in the denominator of a fraction. All right, so this is what we're about to talk about, this feature. We're not allowed to have a radical or a root, right, in the denominator of a fraction. If that's the case, then we're going to have to do something to make it so that it's not in the denominator anymore. Okay, that's called rationalizing the denominator. So rationalizing the denominator is the process of converting a fraction with a radical in the denominator to an equivalent fraction whose denominator is an integer. No more radicals in denominators. Okay, so I'm going to make you see something here. Here I have a radical in a denominator. This is what we don't like. That's an irrational number. It's like pi, it goes on forever. And mathematicians do not like having irrational numbers in a denominator. Okay, so when you see any radical in a denominator, the goal is to get rid of it by doing this process. And it's a quick, easy step to rationalize a denominator with one term. Simply multiply the radical of the denominator on top and bottom of the fraction. All right, so I'll show you how to rationalize 4 over the square root of 3. What we do is take the radical of the denominator and we multiply by that radical divided by itself. Okay, this is the trick. We take the denominator's radical and we multiply that radical divided by itself. Because remember, when you take anything and divide it by itself, that's equal to 1. The square root of 3 divided by the square root of 3 is the same thing as 1. Just like when you take, 2 and you divide it by 2. Anything divided by itself is 1, right? And multiplying by 1 is the same thing. When you multiply something, 4 times 1, 4 times 1 is 4. So that's the idea, is we're multiplying by the same thing divided by itself, which is really like multiplying by 1. Okay, so that's the quick explainer. Now we have to simplify. And so I'll help you. We're going to take 4 and multiply by the square root of 3. That's great. So 4 times the square root of 3 is on top of this fraction. And then we're going to divide it by the square root of 3 times the square root of 3, which is 3. I'll explain. The square root of anything, like a happy college student, times the square root of that same happy college student is equal to that happy college student. So when you have the square root of anything times the square root of that same thing, it's equal to that thing without the square root. Okay? Like, let's say I have the square root of 4 times the square root of 4. Well, that's equal to 4. Done. And with that same logic, the square root of 3 times the square root of 3 is equal to 3. Now I have my answer. This is the final solution. And there is no more radical in the denominator. Now it's just an integer. No more radical. In fact, there's a radical in the numerator, which is perfectly fine. But we cannot have a radical in the denominator. We do not want that. Great. Well, let's move on to the second part of this example, where I have the square root of 3 divided by the square root of 20. So I have a fraction, right, inside of this square root. And so what I'm going to do to begin the simplification process is use the quotient property and split the radical into two radicals, like this. Okay? Now, we can take the bottom radical and use the product property, which says, hey, we can turn one square root into the product of two square roots by finding a perfect square that 20 is a multiple of, right? 20 is a multiple of a perfect square, and that perfect square is 4. And the leftovers is 5. And why did I do that? Because now I can take the square root of the perfect square, in this case the square root of 4, and turn it into 2. The square root of 4 is 2. Okay, so now that I'm here, I look at my denominator and I see, oh no, I've simplified all the way here, but I have a radical in my denominator. The square root of 5 is in my denominator. That's an irrational number, and I never want to have that in the bottom of a fraction. So I'm going to multiply by the square root of 5 on top and bottom of that fraction, like this. Okay? So now that I have done that, I can simplify this radical. And I say, well, the square root of 3 times the square root of 5, I can write that as the square root of 15. Using the product property, I can combine these two roots into a single root, multiplying their radicands together. 3 times 5 is 15. And then I divide that by, well, 2 times the square root of 5 times the square root of 5. And remember, the square root of 5 times the square root of 5 is just 5. And I multiply 5 by 2, and that gives me 10. And now I have rationalized the denominator, and I don't have a radical in the denominator anymore. It's great. Okay? It's rationalized. It's not irrational anymore. All right, so that is an important skill for especially those of you going on to future math courses. Okay, you'll be expected to rationalize the denominator at time for your final solutions so that we don't have irrational numbers, radicals in a denominator. Now, we just did that for square roots, right? We rationalized the denominator for square roots in both cases. So now the question is, what if we increase the index value? And instead of dealing with square roots, we deal with cube roots or fourth roots. So I will quickly show you how I would handle those types of scenarios. All right, so jumping in here to this next example, dealing with cube roots and rationalizing the denominator. Now, here I see the cube root of 6 in the denominator. That's irrational. So I'm going to take the cube root of not just 6, but 6 squared. And I'm going to multiply it on top and bottom of itself. And let me explain why I wouldn't just do the cube root of 6 like I see in this denominator. Because I need 3 of the same thing because I'm dealing with an index of 3. Okay, so I've got a 6, and I need 2 more 6's multiplied together. So that's 6 squared, right? 6 times 6 squared will give me a 6 cubed. And so that will be the thing that rationalizes this denominator. So, this is 6 to the first. I need 3 of the same thing, so I need 2 more 6's multiplied together. That's 6 squared. Okay, I hope my reasoning has helped you to understand this. And so now that I have done that, I'm going to see what the result is. Well, the cube root of 6 times the cube root of 6 squared on the bottom gives me the cube root of 6 cubed, like that. Okay, so looking at my denominator there. And then on top, I have the cube root of 6 squared times 1, right? 1 times the cube root of 6 squared. So I end up with that cube root of 6 squared on top, like that. And the cool thing is, looking at my denominator here, right? The power of 6, right, that exponent 3, is the same as the index value. And so that 3 divided by 3 is 1. The cube root of 6 cubed is just 6 to the first, and I can make that first power invisible. And on top, I couldn't simplify this any further. It's the cube root of 6 squared. Okay? Can't simplify that any further. But it's okay to have a radical on the top of a fraction. It's just not okay to have a radical in the denominator of a fraction. And so we have just rationalized the denominator, and we are happy with this. This is my final simplification. Let me try it with this one. So I have the cube root of 7 over 24. And initially I think, well, I've got to use the quotient property to split the single cube root into 2 cube roots. All right, so we're using that quotient property we've been practicing today, and I get the cube root of 7 divided by the cube root of 24. Great. Now, my brain says right here at this moment, maybe I want to split this 24 into 2 pieces using the product property of radicals. The product property being multiplication. So I could take the cube root of 7 and divide it by the cube root of perfect cube times the cube root of the leftovers. And thinking about 24, it's a multiple of a perfect cube. That perfect cube is 8. 24 is 8 times 3, so I'm going to put 8 in the perfect cube radical and the 3 in the leftovers. Great. Okay, now I get to this point, and I'll write what it's equal to down here. Okay, so I've got the cube root of 7 on the top, and that's divided by, well, the cube root of 8 simplifies to 2. So I'm going to write it as 2. And then I have the cube root of 3. Uh-oh, I still have a radical in my denominator, so I've simplified as far as I can, and I still have a radical in my denominator. So what I'm going to do is multiply the entire expression by that radical in the denominator divided by itself, like this. Because this divided by this is just 1, right? This divided by this is 1, and multiplying by 1 is that same thing. It's cool. Now, there's one extra thing that I need to include at this point. Okay, so I took this thing and I put it on top and bottom, but I don't just need 2 3's inside of a cube root. I need 3 3's. Okay, so I need 3 and then another 3 here to, simplify the radical. So I'm going to include a squared on top and bottom. 3 squared, okay? And now it'll make sense that, hey, I've got, well, on top, the product rule where I can multiply 7 times 9, right? 3 squared is 9, 7 times 9, and I get the cube root of 7 times 9. And that gives me, what, 63? No. 7 times 9, yeah, 63. So it looks like I've got the cube root of 63 on top. And then on bottom, things clean up really well, because I've got 2 times the cube root of 3 cubed, right? Because combining these with the product rule, I would get 3 and 3 squared, which makes 3 cubed. And the cube root of that, yeah. So I've just got 2 times 3 on the bottom, and that simplifies to 6. 2 times 3 is 6. All right, so I've now simplified this, I think, as far as I can, and that's my final answer. Okay, let me move on now, and I'm going to now look at things in terms of perfect fourths, right? So our index has increased from a square root index to a cube root index, and now we have a fourth root index. And so I'll show you quickly how to rationalize the denominator for this case. So when I see this first part of the example, I look at this fourth root of 2, and I say, well, I need to create a fourth root of 2 cubed, because I need to have 2 times 2 to the 4th power, right? My index value is 4, so I get 2 times 2 times 2 times 2. That's why I'm putting 2 cubed right here. And I do that on top and bottom of the fraction. Great. Now that I have things set up, I'm going to do the multiplication. And, this fourth root of 2 multiplied with the fourth root of 2 cubed, you could use the product rule. I'll show you. The product rule would say, hey, multiply the radicands together, and that would give you 2 to the fourth, right? 2 times 2 cubed, 2 to the fourth, right? And then the fourth root of 2 to the fourth, well, the fourth root and the fourth power cancel each other. Or you could think 4 divided by 4 is 1. Anyways, you come to the conclusion that the bottom is just 2 to the first power. That's 2 to the first. Okay, and now looking at the top, well, 1 times the fourth root of 2 cubed is the fourth root of 2 cubed, and we're done. It's okay to have a radical in the numerator. It's not okay to have a radical in the denominator. So we're done simplifying. And now I'll address this radical, the fourth root of 5 over 64. So I've got this fraction in the radical, and my brain says, hey, use the quotient property to split this into the fourth root of 5 divided by the fourth root of 64. Okay, now that I've done that, well, I need to rationalize this denominator. I need to get rid of this radical there. Maybe I can use the product rule to simplify the bottom radical. Okay, so looking at the denominator, can you think of a perfect fourth that 64 is a multiple of? I can. It's 16. 16 is a perfect fourth of the value 2. 2 to the fourth power is 16. And if I multiply 16 times 4, okay, that gives me 64. So here's my perfect fourth, and here's my leftovers. Up top, I've still got the fourth root of 5. Great. And so now this simplifies. The fourth root of 16, I can rewrite it as 2. I'll do it separately. So I have the fourth root of 5 over 2 times the fourth root of 4, like that. And the fourth root of 16 is 2. Okay, next. I still haven't rationalized the denominator all the way, so now I'm going to do it. I'm going to multiply by the fourth root of 4 cubed on bottom and on top. And the question that students always have is, why did you cube 4? Well, because I need 4 4s to be able to rationalize this denominator. Here's 1 4, that's 4 to the first power. And then I need 3 more 4s to make it the value of the index. That's why. But now that I've done that, life's going to be pretty easy to finish off this problem. So looking at the bottom, let's clean the bottom up. Okay, the denominators, this is going to be 2 times 4. That's just 2 times 4. Because the fourth root, when I use the product property here, the fourth root of 4 to the fourth is just 4. Okay. And then on top, I have the fourth root of 5 times the fourth root of 4 cubed. And so I'm going to use the product property here, the fourth root of 5 times 4 cubed. Right? 5 times 4 cubed, like that. So that doesn't simplify really at all. And so I'm going to multiply 5 times, I'm going to have to multiply 5 times 4 cubed, which is 5 times 64. And so I'll get out my calculator, kind of bigger numbers. 5 times 64, I think is 320. Let me make sure. Yep, 320. Okay, so I've got that. And then 2 times 4 is 8. And we've done it. Man, that was a real brain twister, wasn't it? So we see rationalizing the denominator is relatively easy when we're dealing with square roots. And then it gets a little more complicated on our brains when we're dealing with cube roots. And then, wow, fourth roots. Pretty intense. I at least want you to remember how to handle square roots, okay? Because that is what will come up most often. Most often in other courses, you're dealing with square roots instead of cube roots or fourth roots. Now, to finish our lesson today, our final objective is to rationalize a two-term denominator. To rationalize a denominator with two terms, like this, look at this denominator. It has not one term, but two terms in it. Terms are separated by addition or subtraction. So the first term is 2, and the second term is root 3 with subtraction between them. Yeah, and here it is again, and this one again. So to rationalize a denominator with two terms, multiply the conjugate of the denominator on top and bottom of the fraction. Now, a little reminder for you, conjugates, okay? When you have two terms, like A and B, let's say, and let's say you have addition between them. Well, the conjugate of A plus B is taking those same two terms, A and B, and putting the opposite sign between them, subtraction. So if you have the same two terms with opposite signs between them being multiplied together, those are conjugates of each other, right? A plus B is the conjugate of A minus B and vice versa. So what we're saying is to rationalize this denominator that has a radical in it, we need to multiply the top and bottom of this expression by the conjugate of the denominator. All right, so I'm going to do it with you. We see 2 minus the square root of 3, and so we're going to multiply the conjugate on top and bottom, 2 plus the square root of 3. Great, we did it. Now we need to simplify, okay? So let's do the multiplication. Now to multiply the numerators stuff together, we would be multiplying 5 into the first term and second term. And 5 times 2, that gives me 10. And 5 times the square root of 3, well, that's just 5 times the square root of 3. It doesn't simplify any further than that. Okay, so I just multiplied 5 into both these terms. 5 times 2 is 10. 5 times the square root of 3 is the square root of 5 root 3, and I've got addition between them. Let's address the denominator. And we notice we have a binomial times a binomial, so we need to FOIL, right? To multiply two binomials together, we FOIL. That's first, outer, inner, last multiplication, like we're used to with two binomials. And so I take the first terms, multiplying them together. 2 times 2, that gives me 4. Let me do it in blue. All right. Now, outer terms, 2 times the square root of 3. They're both positive, so I get a plus 2 root 3. Okay, moving on. The inner terms, we're going to multiply them together now. Negative root 3 times 2, that's a minus 2 root 3. And then let's multiply the last terms together. Negative root 3 times positive root 3. And at this moment in time, remember when you're dealing with square roots, we can use this idea that the square root of a happy college student times the square root of a happy college student is a happy college student. Okay? So if I see the square root of 3 times the square root of 3, my brain says the answer is just 3. Right? Let me do it. The square root of 3 times the square root of 3 is just 3. And so that's why I'm going to put here a minus 3. Why minus? Why is there a minus? Because I multiplied a negative by a positive, so I got a negative. Okay? Great. And so now we're at this point, and the great thing about conjugates is that the outer and inner terms of foiling, when you FOIL conjugates, those terms are opposites of each other. Same value with opposite sign, right? I had positive 2 root 3 and negative 2 root 3, so they always cancel. The outer and inner terms of foiling always cancel when you're multiplying conjugates. And so my final result is on top 10 plus 5 root 3. That doesn't simplify any further. But look what happens now. I now have a 4 minus 3, and that's just 1. That's an integer on the bottom. We don't have any radicals on the bottom anymore. Yeah, that's what we want. No radicals in a denominator. Our denominator has been rationalized. Now, one last idea is that, hey, when you divide by 1, that can become invisible, right? Division by 1 or multiplication by 1 becomes invisible. So my final answer can simplify to look like this. Great. Well, let's go ahead and look at this next example, 8.54. And in the denominator, we see radicals, gross. And we see that there are two terms separated by subtraction, right? We have the square root of u is the first term, square root of 6 is the second term. And so our trick is to multiply the expression by the conjugate of the denominator, which the conjugate of this denominator would be the square root of u plus the square root of 6, right? Opposite sign, right? The conjugate of the, subtraction has addition. And so I'm going to multiply the square root of u plus the square root of 6 on top and bottom. Because remember, taking one thing and dividing it by itself is just 1. Anything divided by itself is 1. And multiplying by 1 keeps this thing the same. So it's really the same thing. And so now I will proceed to simplify. And I'm going to be multiplying the square root of 3 into both of these terms here and here. Okay. And so the square root of 3 times the square root of u, I can write it as the square root of 3u. Using the product rule, I can combine these two. I'm multiplying these two radicals together, so I can combine them to a single radical, taking their product under the radical in the radicand. Okay, now I move on to the square root of 3 times the square root of 6, right? And that's the square root of 3 times 6, which is the square root of 18. Now this can be simplified. The square root of 18 can be split apart into two radicals. The square root of 9 times the square root of 2. Because 18 is a multiple of a perfect square, and that perfect square is 9. So I'm going to turn the square root of 18 into the square root of 9 times the square root of 2. And then I'll turn the square root of 9 into 3, because that's what it is. The square root of 9 is 3. Great. So cleaning this up a little bit, I have 3 times the square root of 2. That's the result of the square root of 3 times the square root of 6. By the way, if you have a TI-30XS calculator, it will simplify radicals for you as long as those radicals do not have variables in them. Okay? So if you took the square root of 3 times the square root of 6 in your TI-30XS calculator, it would simplify it to 3 root 2 for you. That's good to know, isn't it? Now, moving forward, we have the square root of u times the square root of u. The square root of anything times itself is equal to that thing, right? Let's go back. The square root of a grumpy college student times the square root of a grumpy college student is equal to a grumpy college student. So when I see the square root of u times the square root of u, because I'm foiling, right? I'm multiplying first, outer, inner, last terms together. Then I just think, oh, that's u. All right, so that's my start. So the product of my first terms of the binomials is u. Moving on, I now have to take the square root of u and multiply it with the square root of 6 as outer terms of foiling, the outer terms. And so I get plus the square root of 6u. I use the product rule to combine two radicals into one. Okay, now the inner terms of foiling. So negative root 6 times root u. Use the product property that we've been using, and you would get negative root 6u. And lastly, we have negative root 6 times positive root 6. And just think root 6 times root 6 first, yeah? So root 6 times root 6 is 6. And because we were multiplying a negative by a positive, the result is negative 6. Great, we got to this point. And just like previously, how we saw the outer and inner terms of foiling cancel each other when you multiply conjugates, it happens again. Look, positive root 6u and negative root 6u are same value, opposite sign, so those cancel. Which means we have just rationalized our denominator. No more radicals in the denominator. And so we'll write our final solution as the square root of 3 times u plus 3 times the square root of 2 divided by u minus 6. Done. Great. Okay, perhaps we just try this one last time. Okay, so just, it's good to practice. So I'm going to jump in here and I'm going to do the same thing I've been doing. I'm going to look at the two terms of this denominator and say, well, I am going to multiply top and bottom by the conjugate of that denominator. And the conjugate of the denominator, just write the first term and the last term. Yeah, of that denominator. So I wrote the first term and the last term. And then do the opposite sign of what it shows, right? Opposite of subtraction, that's addition. Good, you wrote the conjugate. Now just copy it on the bottom. And anything divided by itself is 1. So this thing that we have right here is really just multiplication of 1. And now we are going to multiply all the binomials together. So we'll multiply the top binomials together and the bottom binomials together, and we'll get a result. And to multiply them, yeah, we're going to be foiling the top and also foiling the bottom. And so I'll talk you through that process. The square root of x times the square root of x is just x, because the square root of grumpy college student times square root of grumpy tired college student is grumpy tired college student. Okay, and so now we proceed to multiply outer terms together, and you would conclude that we get a plus root 7x when we use the product rule, right? Product property. We're just going to take these two radicals, combine them into one by taking the products of the radicand. Now, inner terms. Well, I see root 7 times root x again, so I'll do the same thing. I'm going to have plus root 7x. And then let's multiply the last terms together. I have positive root 7 times positive root 7, and we get a plus 7. Cool, let's look at the denominator, and let's FOIL the denominator binomials, right? So root x times root x, x. Root x times root 7 is positive root 7x. Okay, now inner terms. Negative root 7 times root x is negative root 7x. And last terms, negative root 7 times positive root 7 is negative 7. And since we multiplied conjugates together in this denominator, the outer and inner terms of foiling cancel each other, just like has happened with the previous examples. You guys see a pattern? The outer and inner terms of the denominator conjugates, when you multiply them together, they cancel. And so we're going to get our final answer here of this lesson. And simplifying everything, I see an x. And then I see like radicals. Like radicals have the same index and the same radicand. Look, same index, same radicand. So this 1 root 7x and this 1 root 7x add together to make 2 root 7x. Okay, and now lastly I have this addition of 7 at the end, like that. And now my denominator is just x minus 7. I have rationalized the denominator. There are no more radicals in my denominator. It's great. All right. So in this lesson, going backwards, we have rationalized the two-term denominator. Yeah, when I have two terms, just take the conjugate and multiply by the conjugate on top and bottom. We have rationalized single-term denominators. Yeah. So here was the example with square roots, then cube roots, then fourth roots. And we have also used the quotient property to divide two radicals, one from another, as long as they have the same index value. And so there we go. That was all that we practiced today. Thank you so much. I hope you have a great day, and I'll see you in the next one.